Hello, everyone. My name is James Chibueze from Northwest University, Potchefstroom in South Africa. I'll be giving this lecture on error recognition, mostly on interferometric calibration and imaging. And the credits are given to Joe, who prepared these slides. I've made a few additions and a few minor changes. And yeah, we get along with it. So this lecture is with the assumption that you've taken a lecture on basics of interferometry, and then you do understand how to do calibration and how to attempt to clean or what you call Fourier transform the visibilities you've calibrated to make an astronomical image from your radio interferometer. But the key question here is, how do you recognize when something has gone wrong with your calibration or imaging? Do you just raise your hand and say, I don't know, I don't care, it is what it is, or I don't know where to sort the problem from? So this lecture is aimed at helping you troubleshoot your image and be able to pin down what the possible cause of the problem you see in your image plane is, and how you could fix it in the visibility plane even before you do the imaging. So some of the key questions we want to answer is, how do I know I have bad calibration? What exactly could be the problem? Could it be RFI, or could it be something like bad phase solution interval? Or can I have a problem with smearing, which comes from averaging either in time or in frequency? How do I know what is making my image bad? It is important for you to note that most of the errors you encounter, apart from errors associated with the clean, these errors occur in your UV plane, or what you call your aperture plane, not in the image plane. Generally, bad calibration could be seen when you plot your visibilities, or you try to check what is happening to the visibility amplitude over time. Or you try to look at your amplitude plot against your UV distance. For example, in this image, if you look at this amplitude versus time plot, everything looks quite fine around this time range. But if you look at this particular time range, you will see that there are visibilities jumping in amplitude and are very strongly lower than the expected amplitude. So in this case, something must be wrong around this time range. It may be a bad antenna showing bad amplitude scale. It could be anything, but you have to track it down and take it out. Again, if you make a plot of the amplitude against the UV distance, in this case, UV distance in giga wavelength, because we present UV distance as a function of the wavelength. So you want to present your baseline length as a function of the wavelength at which the observation is carried out. And you also see these clear-cut outliers. Well, you may worry that there is this decline as you move towards longer baselines. The implication of this is simply that you are beginning to resolve the object until it just flattens out. Maybe you don't resolve it anymore. But this is not your problem. This drop here that you see is actually not the problem. The real problem you have is this outlying amplitudes that is bad. Good. So if you cross-check your different antennas and see how each one of the antennas in your array is behaving, and you spot, say, antenna 7, like in this case, that has a problem in its amplitude, and flag that antenna, then if you make this plot again, you will see that everything looks fairly good now. You don't have those outliers again. So that's one way you could find problems in the calibration by just plotting out your calibrated visibilities in amplitude and in phase. However, finding such problems could be extremely difficult when you are dealing with very weak sources. In this case, you have a very strong source, which goes as high as 10 Janskis. This is an extremely strong source. But in this particular case where you're dealing with a few hundreds of millijanskis brightness of a source, then it becomes a problem to know what exactly is an outlier here. Of course, if you assume the source is somewhere around here, which you could say is about 75 millijanskis, it's difficult to say if these are something here is an outlier or something there is an outlier. You don't know exactly where to cut off and treat an outlier. One possibility, of course, the obvious cases are these ones that are really high up here. You're almost 100% convinced that these are outliers. But one of the practical ways you can do this is just to remove everything that is 3 sigma, 3 times what you think is the flux of the source or the amplitude of the source multiplied by 3, and then you draw a line and flag everything else. So now if you're dealing, if you want to find out what went wrong in terms of your calibration in the UV plane, it can be quite difficult to spot sometimes in the UV plane, as I've just shown you, that if you're dealing with a weak source, it's difficult to see. You may also not see the bad calibrations in the phase in the visibility plane. So sometimes you may need to look to the image plane, which is a Fourier transform of your visibility, to be able to spot exactly what the error is. So how you identify this is by looking at your image and looking for structures that are strange. They usually come in form of patterns. It could be streaks. It could come as rings. Some of the structures are very symmetric. Okay, so if you find symmetric structures like something that if you have a central source here and there is a source that you can measure the distance from the source here to this point, and there is another thing here that is almost an equal distance from here to here, then you say that is symmetric structure around your object. That is an easy giveaway. If you see these symmetric structures, you can quickly tell that there is something wrong with the calibration. The equation to define the exponential function of I phi, of course, you can split this into sine and cosine function. And if your image is symmetric, then the real even part gives you symmetric, real and even part gives you symmetric image errors, which is most often attributed to amplitude calibration errors. If it's real and odd, which simply gives you the imaginary side and odd, then this is non-symmetric, which you call asymmetric errors, which is mostly due to phase calibration errors. To show you this in the what this will look like in the image plane, if you look at this image, which has a 10-degree phase error, then you will see the main object and you see these bright lobes or bright object or asymmetric ridge, but you don't see the same thing on this side. You don't see this brightening. So that's how you can tell that this effect, which you are almost 100% convinced is calibration error, is non-symmetric or asymmetric. And this is due to phase error. However, if you look to the other side, where the image of a calibration that has 20% amplitude error, then you can see the bright object in the middle, and you see a pattern, and you can reproduce symmetry between this side and that side. So you see symmetric effect of this brightening is almost like a line, and you can see the small dots will always reproduce its counterpart on the other side, having symmetric effect on each side. No matter how deep you clean, you will still have problems or effect of the beam pattern. So, but most times the errors you see here, like the amplitude errors, you can always get rid of if you improve your amplitude calibration. And that can be done through self-cal as well. You see that later on. You can have two images like the ones presented here. This is persistent error over most of your observations could come as a result of error in phase or error in your amplitude calibration. These can nearly mirror each other depending on the quantity or the size of the errors you produce. Like on the left-hand side, if you have a 10-degree phase error for one antenna all the time, this will introduce an RMS of 2.0 millijanskis. And of course, you can see these phase errors in the asymmetric structures you see around this image. That would be almost similar to when you have 20% amplitude error for one antenna all the time, and that will give you also a around 2 millijansky, which 2.3 millijansky RMS. But in this case, every of these side lobe looking ring structures would be very symmetric. Okay, so how do you deal with this problem, especially when you are carrying out the task clean for your data set that you have nicely calibrated? If you look at the image provided on this panel, this is your DATI beam or your DATI image without any cleaning. So if you produce this image, and of course you can tell that the source of interest lies somewhere here in the middle, and you want to add clean box. In practice, many people will put very large clean box over this region and you extract the clean components. But the problem with having big clean box over this is that you are also cleaning the dips or the noise area, and you will produce this image. If your clean box is an image size, middle size clean box like this size, then you reproduce this image. But if you put a clean box just around the main source or the main source of the emission, you can tell, for example, what is side lobe. This blob here is symmetric to that blob there. That one there is symmetric to this one here. So you can tell this is something about the amplitude calibration. So if you put a clean box that covers that area, it retains that emission, the side lobes or the wrong amplitude correction, it retains them in the final image. But if you keep a clean box around here, you'll be able to produce a better quality image. There is a practice that gives you even far more better quality image, which is, for example, using CASA. You could try to trace out the emission blobs, which gives you an irregular shape of clean box, not a rectangle, not an ellipse, which will have some extra area not covering the main target of interest. So you can actually retrace the morphology of the source with the irregular clean box pattern from CASA, for example, if that is what you use. So you want to make your clean box as small as possible to avoid cleaning noise that is interacting with your side lobes. That's simply what it is, so that you get a good quality image in the end. One of the main problems you face in running the task clean in order to Fourier transform your visibilities to the image plane is that you run the risk of either under cleaning or over cleaning. If you under clean, one of the real problems is that you retain these residual side lobes that dominate the noise. And if you over clean, then you have things that are modeled up. You have strange looking emission around your real target. If you over clean, also sometimes you get dips in practice. You get some extra dips all around. So you want to just clean to the appropriate level until you get your background noise level to be equivalent to the thermal noise that you expect from your array. In that case, you will not see any negative balls within your data. Negative balls are these areas such as this, where you have negative intensities. Okay, so if you find this kind of thing in your image, you have undercleaned. If you find your source being modeled, sometimes showing unreal fragments looking kind of thing, then you have overcleaned. So you want to always check these structures in your final image. Okay, when we talk about negative balls on the cleaning, this is one example that shows you that you would start seeing, for example, in this wide field imaging with multiple sources, or the darkened area which has negative intensities are what we call negative balls. And these are evidence. You see it all over all the bright, some of the compact point sources. If you see this, just know that you haven't cleaned deep enough. And one way of knowing whether you have undercleaned is to zoom into some of the negative balls for any of the point sources. If it looks similar to your point spread function, your PFS, you will always get, for example, if you run this in CASA, you will always get it as whatever name of the file, .image.psf. This point spread function, which is equivalent to what you have for your beam that you use to recover the real emissions from your image. So if you can find this pattern to be similar to what you see after your clean, then you know that you have really undercleaned. However, if you find some streak of pattern in your image, for example, having this almost symmetric lines pointing this way, then you have some radio frequency interference. So that I will show you another example. You could have this sort of interference coming from, depending on the wavelength at which you observe, it could come from satellites, if not properly flagged. It could come from even the sun, if it filters into your side lobe. And I'll show you an example from Meerkat. Okay, so one of the rules, that general rule of thumb you want to follow, is that we always use phi sigma to believe a structure is real. So if you reach 3 to 5 sigma in the theoretically predicted noise level, then that is likely a real source. And how do you determine what sigma is? Sigma is just your root mean square noise. And theoretically, that is 2 times K, which is a constant, multiplied by the system noise temperature, divided by the effective area of your aperture. Now that you are dealing with an interferometer, that will be divided, multiplied by the square roots of your number of antennas, multiplied by number of antennas minus 1, multiplied by the integration time, multiplied by your bandwidth. So all these in square roots. So this is how you determine your noise level, and 5 sigma would be a structure or an emission that you will believe. The errors we find are effects in bad data points within our visibilities. Could be some kind of additive artifacts or multiplicative ones. So, of course, if you want to detect weaker emissions, if you're looking at this equation, you want this value to be very, very small so that 3 to 5 times this value would be detected. For example, if you want to detect a source that is 5 millijanskis, then you want your noise level to be somewhere around 1 millijansky. Okay, so one way to do that is to reduce this value, you want to increase everything in the denominator. So you either increase the effective area, okay? You want to increase this value, or you increase the number of antennas, which is N. If you're not able to do that, you want to observe for a longer time, which means you have to increase your integration time on source. If you're not able to do that, then you could also attempt to increase your bandwidth, use a wideband receiver. In the case you're not able to do any of this, then you want to, if you don't have a cryogenically cooled receiver, you want to find a low noise receiver system, or try to cryogenically cool your receiver system so that the noise coming from the receivers will be lower. Therefore, your TCs will be smaller in size. Could go down to a few tenths of Kelvin, depending on which instrument you're using. So that way you can improve your root mean square noise and be able to detect weaker sources. So that brings us to the point astronomers always use very often, which they call dynamic range. Remember that astronomers always want high dynamic range. Dynamic range could have various definitions. In this case, if you have a source, first you want to determine what is your root mean square noise, right, in the interferometer. So to do that, you want to take the noise level around an area in your image which has no emission-free area. In practice, it's best to take emission-free area near your source or near the center of the image. Some astronomers would take root mean square noise of the center of your primary beam. Okay, good. So you derive your noise level in this case, which is defined as sigma, and in this case is derived to be 27 microjansky per beam. And then the next thing you want to determine is the peak flux of the target of interest, be it this one or that one or this weak one. So if you find the peak flux of this, for example, is 2 Jansky per beam, and then you can take the ratio of these two, divide 2 Jansky per beam peak flux by the RMS. So peak flux over RMS is what gives you the dynamic range. And in this case, you can see it's actually 74,074. And that is a very good dynamic range. The higher, the better. But assuming you did not clean your image or do a proper cleaning, or maybe you didn't perform self-calibration, then the quality of this image will be poorer than you have it. And one of those examples is this. So if you have this kind of image as your final image, then there is an alternative definition of dynamic range which we're going to use. And that could be the peak of the flux, okay? Peak of the source of interest divided by the peak of the artifact. You can see the artifact all around this source. If you take the peak of one, this is in millijanskis, because it's an interferometer, I think this will be millijanskis per beam, and that is Jansky per beam. And you can divide the peak flux of your source divided by the peak of the artifact. And in this case, you will get a ratio of 370. This is still an obvious detection, but you can see the dynamic range is quite low. And just saying the dynamic range, we can tell astronomers, experienced astronomers can imagine what the quality of your data is. If you do that for even a weaker source, then the dynamic range will become far lower than this. Like in this case, if that is the main source and you use that as the peak artifact, this is almost close to this. It's probably less than 4 or 5. I don't know. I don't have the image. I would have calculated it myself. Okay. And assuming you apply self-cal with 5 minutes integration time, solution interval to the previous image I showed, then you will be able to come down to an RMS of 58 microjansky per beam. I added per beam in the previous one. I haven't added it here. And if you take the dynamic range, you are now at 34,000, which is almost half the dynamic range we had in the previous one. So if you do, say, another cycle of self-cal, fits in a few more of the phase and amplitude. If you use phase and amplitude mode and do another cycle of self-cal, you will improve this RMS a lot more. Probably get it to the quality of this one. I want to note that self-calibration is an iterative process. If you apply the initial phase self-cal and you're not, of course, the image dynamic range will improve. You want to try another cycle, maybe reducing your solution interval and still do it in phase. And you want to try again with phase and amplitude mode to get a better, more improved image quality. Okay, so I've earlier mentioned that the errors you get in your visibility could be additive, in which case it adds to your visibility, or it could be multiplicative, in which case it multiplies or convolves into your visibilities. And these are just equations to demonstrate that it could actually be an additive error to your visibility, or it could be a multiplicative error, or what you call a convolved error within your visibility. And to illustrate what this could look like, of course, additive errors has nothing to do with your real sources. They come as fake sources within your image in your image plane. And these sources of this could include noise, it could include RFI, it could become some kind of confusion or things like the sun that gets into your side lobes. It could also be some direct current offsets, or DC, what you call DC offsets. One example I have just taken from one of my Meerkat observations is the effect you will have if you are observing a source that is very, very close to the sun. So these nice patterns you see here is the effect of the strong radiation from the sun getting into the side lobes of your beam. Remember, your beam has a main lobe and the main lobe in the middle, and then the side lobes on the sides. If you put your main lobe a few degrees, in this case is actually 2.5 degrees away from the sun, pointing the Meerkat telescope, then your main lobe is pointing 2.5 degrees, but the side lobes pick up radiation from the sun, and you see this. What you're seeing in this pattern is actually just the sun entering the side lobes, and it's so strong that it dominates the entire image. Of course, fixing that is quite difficult, but it can be done. I have described the multiplicative error. Example are things you have in your sampling rates. You could also have errors in your gain calibration, errors in the atmosphere, what you call missing spacing or missing flux, because the antennas in your array are spaced out so much that you have these additional gaps, which leads to missing flux problem. The convolution or the errors that convolve with your intensities include things like your primary beam correction and problems with convolution problems with gridding. Okay, so to describe things a bit more, phase errors and how these apply to your dynamic range. Imagine your image, the image that is formed in the Fourier transform space is given by this equation right here. This means that each baseline will contribute at any position u of k and some complex conjugate of this minus u of k in the visibility plane. Now, if you evaluate this term in the integral for each of the baselines, then every good baseline will provide you 2 times the cosine of this function. That's 2 pi u of k x. However, on the contrary, every bad baseline would give you this same solution, in this case, u of 0, minus the phase error. Okay? The phase error, a small phase error you see. So this gives you a solution represented by this small equation, where the small phase error is in radians. Now, if you put that in the image integral, then you are going to have a solution in the image plane with some 2 phi e, which is the phase error included in the image plane. Okay, so if you consider the synthesized beam, which is given by b of x, which is 2 times the sum from k equals 1 to all baselines over 2. And then you have this cosine of 2 pi u of k of x. then for U equals, this will give you your total number of baselines if U is 0. Okay. Because if U is 0, then this whole cosine of 0 becomes 1, and that's the entire solution you have, right? Okay, so if you want to do the deconvolution, it simply means you're trying to subtract the beam from the image, just leaving your residual error. And if you write that in form of equation, then this is the equation you get, and that leaves you with this additional phase error coming from the amplitude correction. So you get an odd sinusoidal function of amplitude with 2 phi e, and then the period of this in the solution will be the reciprocal of u of 0. So for this small phase error and very large number of antennas, then the ratio of your peak flux over the noise residual is actually the square of the number of antennas divided by the square root of 2 times this phase error you have. So a 5-degree error will give you 0, or what you call, it will give you, which is 0.009 radians, right? Okay. So amplitude error on a single baseline has the effect given by this equation, which leads to a dynamic range of this error, which is what's similar to what has been given here. Okay. So to illustrate what we call smearing, which is another kind of error you get from averaging in time or in bandwidth. Bandwidth smearing is just similar. Sometimes we call it frequency smearing. So if you average so much, it affects sources that are off the center, and it just makes them look blobby or could make them get stretched. The farther away it is from the center, the more effect from the pointing center, the more effect it has on the sources further away, depending on how much you average in time or in wavelength, or in bandwidth, sorry. This is an example of time smearing effect, which is shown right here. And the other problems you could have is the issue of missing short baselines. If you have very long baselines, they become very sensitive to compact sources. So if you have very extended sources, then you need your short baseline, because those are what will become sensitive to your extended sources. So what you see in this image is your short baselines being sensitive to these extended structures of emission. And when you remove your short baseline and have only long baseline, you reproduce the compact emissions, but the extended emission is completely lost. So if you have no short baseline antennas, be sure that that's the price you pay for having an interferometer, is that without the short baselines, the extended structures are completely lost. The other problems you could have is what we call direction-dependent effect, or direction-dependent calibration problems. These arise from having a bright source within your field. And these bright sources, remember, a bright source will interact with the main lobe of your beam, right? And will as well be visible in the side lobes. If you remember, I guess in the lectures for basic radio astronomy, we are shown that antenna's response has a main beam and has side lobes. If your source is bright, or if you drive your beam to a source, it interacts first with the side lobes. And then, for example, those who do drift scans, you will see the first null. Of course, you will see the side lobes, and then you meet the first null, you meet the response to the main beam, you see another null on both sides, and then you meet the response on the side lobes. So if you have a bright source like this one within your field, and this interacts with your side lobe, is going to produce this symmetric bright side lobe effect that will spread all over and could contribute to the problems you have in the flux measurement for other weak sources that are within the side lobe. You can tell that there is a bright source on this corner that produces this side lobes pattern that you can see. Depending on the brightness of the source, the spread of the impact of the side lobe vary. For example, this very bright source have, well, there is even a brighter one down there that we can't see, but it has a stronger impact. This one has effect up to, from what I can see in my eyes, up to this point. But you can also see that this has a direction, a side lobe effect, and you can see those streaks of lines coming from this. Because this is weaker, the effect is limited. The effect of this one, it does not reach, has no effect on this source here because it doesn't get here. But the effect of whatever source is hitting that side does come to sources around here. The effect of this gets to these objects right here. The effect of this gets to that object. There seems to be a point source there. It affects that source there. And this, well, definitely affects the flux measurements you have and your interpretation of your science. There is also another problem we call sleuthing. This comes as a result of finding some strange shapes, which comes from not maybe doing proper self-cal and so on. You can see this sleuthing effect due to your beam. If you go back to your point spread function, you would see that this pattern would nearly mirror that point, would be very similar to your PSF. And if you simply apply one iteration of phase self-calibration, you can see things start getting much better. Okay, so that is where I will stop the lecture. The rest of the things here is for you to exercise your brains to see how well you understood the things I have said so far by trying to identify the kind of problems you see. For example, what sort of error do you see in this particular image? Because this is meant to be an interactive section, I will just show the different kinds of errors, and hopefully over Slack interaction, or when you have real-time discussions via Zoom in the real-time interactive sessions, then we can revisit these problems. Okay, so that is one problem. What do you think is the problem here? This is MWA, low frequency observation. Do you think this is heat haze? Do you think this is coming from antenna deformation, or do you think this is ionospheric problem, or is this compression artifact? What about this? Is it some amplitude error, or is it cosmic ray? Is it bandwidth smearing, or is it RFI? What about that? Is that amplitude error or phase of moon that is incorrect? Or is this a position dependent error? Is it source outside imaged field? Is this amplitude error, or is it Titan from wrong clan? Is this some alien or data stored in hex? Or is this phase errors? Okay, so that's where I will stop. And hopefully in the interactive section, we can have more interactions and I can respond to questions at that time. Thank you very much for listening and talk to you sometime soon.